Hello, Accelerated Chemistry. This is Ms. Christopher, and this is your Chapter 13, Section 1 video notes all over the nature of gases. So we're going to start off by talking about the kinetic molecular theory, which is a model for gases. So the word kinetic refers to motion. So the energy an object has because of its motion, it calls it kinetic energy. According to the kinetic theory, all matter consists of tiny particles that are in constant motion. So the particles in a gas are usually molecules or atoms. The kinetic molecular theory states that the particles in a gas are considered to be small, hard spheres with insignificant volume, which means they have no volume. Within a gas, the particles are relatively far apart compared to the distance between particles in a liquid or a solid, and between particles there is empty space. So that means that there is no attractive or repulsive forces that exist between the particles. So that means that there are no intermolecular forces that exist between those particles. The kinetic molecular theory also states that the motion of particles in a gas is rapid, constant, and random. So this means that the motion allows for gases to collide with one another as well as the walls of the container. And gases will fill their container regardless of the shape and volume of containers. An uncontained gas can spread out into space without limit. The kinetic molecular theory also states that the rapid, constant motion of particles in a gas causes them to collide with one another in the walls of their container. The particles travel in straight line paths until they collide with one another, and the particles change direction only when they rebound from collisions. And finally, the kinetic molecular theory states that all collisions between gas particles in a gas are perfectly elastic. So that means that during the elastic collision, kinetic energy is transferred without the loss from one particle to another. And so the total kinetic energy is going to remain constant. So now let's talk about gas pressure. Gas pressure results from the force exerted by a gas per unit surface area of an object. So moving bodies exert a force when they collide with other bodies. Gas pressure is the result of billions of rapidly moving particles in a gas simultaneously colliding with an object. So if no particles are present, no collisions can occur. Consequently, there is no pressure. An empty space with no particles and no pressure is called a vacuum. So air exerts pressure on Earth because gravity holds the particles in air within Earth's atmosphere. So the collisions of atoms and molecules in air will, with objects, result in atmospheric pressure. Atmospheric pressure decreases as you climb a mountain because the density of the Earth's atmosphere decreases as the elevation increases. So when we look at a barometer, which is the picture to the right, it is a device that is used to measure atmospheric pressure. So at sea level, air exerts enough pressure to support 760 millimeter column of mercury. On the top of Mount Everest, 9,000 meters, the air exerts only enough pressure to support a 253 millimeter column of mercury. So the SI unit for pressure is pascals. Normal atmospheric pressure is about 100,000 pascals, and that is 100 kilopascals. And then there are two older units of pressure that are commonly used: millimeters of mercury and atmospheres. So you can imagine that we are going to have to do some pressure conversion. So here we go. One standard atmosphere is the pressure required to support 700 millimeters of mercury in a mercury barometer at 25 degrees Celsius. So the numerical relationship among the three units are 1 atm is equal to 760 millimeters of mercury, which is equal to 101.3 kilopascals. So recall that standard temperature and pressure, STP, are defined as the temperature of 0 degrees Celsius and a pressure of 101.3 kilopascals, or 1 atm. So let's look at an example problem. Let's convert between pressure units. So a pressure gauge records a pressure of 450 kilopascals. We're going to convert this to atmospheres and then to millimeters of mercury. So as always, we have to list what we know. So we know the pressure, and we know some conversions. What we don't know is what the answer is in our new units. So now we are going to solve for unknown. So we're going to identify our conversion factors. So we know that we have 1 atm for 101.3 kilopascals. And we know that 760 millimeters of mercury is also equal to 101.3 kilopascals. So we're going to set these problems up so that they cancel. All of this setup should be you should be used to because we've done it numerous times. So your answer for A should be 4.4 atm, and your answer for B should be 3,400 millimeters of mercury. So Because the first conversion factor is much less than 1 and the second is much greater than 1, it makes sense that the values in ATM and millimeters of mercury are going to be smaller or larger than what they are in kilopascals. Let's talk about kinetic energy and temperature. As a substance is heated, its particles absorb energy, some of which is stored within the particles. So the portion of energy or potential energy does not raise the temperature of the substance. The remaining absorbed energy speeds up the particle, and that will increase their kinetic energy. So if you increase the kinetic energy, you're going to increase the temperature. So when we're looking at average kinetic energy, the particles in any collection of atoms or molecules at a given temperature have a wide range of kinetic energies. Most have kinetic energy somewhere in the middle of this range. We use average kinetic energy when discussing the kinetic energy of a collection of particles in a substance. Because remember, we cannot take the energy reading for just one particle. We're going to look at a sample, which is going to have Avogadro's number or even more of those things. So at any given temperature, the particles of the substances, regardless of the physical state, have the same average kinetic energy. So if we were to look at this distribution, we're looking at the percent of molecules versus their kinetic energy. So at lower temperature, we're going to have more particles that are going to have a lower kinetic energy. And at higher temperatures, we are going to have more particles that have a wider range of kinetic energy. So if we were to look at this distribution curve, if you have colder particles, they're going to be tall, skinny peaks when we look at the number of molecules versus the energy they have. If we have a lot of particles, they're going to be short and a little bit wider because they have more particles that have a wider range of kinetic energies. So the average kinetic energy of the particles in a substance is directly related to the substance's temperature. So an increase in the average kinetic energy of the particle causes the temperature of the substance to rise. And as the substance cools, the particles tend to move more slowly, and that's going to decrease their average kinetic energy. And remember, absolute zero or 0 Kelvin or negative 273.15 degrees Celsius is the temperature at which the motion of particles theoretically ceases. So no temperature can be larger than absolute zero, and absolute zero has never been seen before in a lab, but we've gotten to 0.1 nanokelvin. And so the coldest temperatures that we have recorded outside of the laboratory are in space, and astronomers use a radio telescope to measure the temperature of the Boomerang Nebula, which is shown to the picture to the right, and at about 1 Kelvin is the coldest known region of space. So to sum it up, average kinetic energy and Kelvin temperatures. The Kelvin temperature of a substance is directly proportional to the average kinetic energy. And as always, all the information on these Google Slides has been acquired and adapted from Pearson Chemistry's 2012 edition textbooks, resources CD, and pearsonchem.com. Thank you so much. Have a great night.